So remember last time I taught, we did some work with acceleration and velocity and displacement, and we had these two toy cars, and we had their acceleration functions, and we were interested in finding velocity, and how were we able to write a velocity function given an acceleration function? Where is Caitlin? Integral to acceleration, right? Because we want to what? Accumulate changes in velocity, right? And change in velocity is acceleration, right? So if we accumulate changes in velocity, and that's what acceleration is, it's our change in velocity. Accumulate little changes in velocity, we'll build the velocity function. So there those are. And so then in this GC file, I have graphing both of those. So we had the acceleration of car 1 and car 2, and then over here on the right is the velocity. And now I want to graph the displacement of the cars, or the distance traveled by the cars. And how will I do that? How will I build a function to get the distance? Where is Michael Hilby? Integral of the velocity, right? Because we're going to accumulate little changes in distance. And we know that velocity is giving us change per distance, right? It's giving us how much change there is per unit distance. So if we accumulate changes in distance. So here we go. Let's watch GC do this. So here's the acceleration over here. Here's the velocity, which is the integrals of acceleration. And then we can get distance by doing integrals of... So here we go. So then I've got the distance is integral of velocity. And if you stuck around in class that day, as we were wrapping up, I think we all got to see what happens when we graph this. Here it goes. Did I have both of them? I don't think I have both of them. Hold on a second. So that you saw how slow that one went, and I think I have to. All right, here we go. The other one as well. Oh, again, I got to do them both again. All right, so you put a load of laundry in, make a sandwich. So what's going on here? Why is this taking so long? Yeah, Scott.
Well, it's taking the integral of the acceleration function and creating a really long list of values to give for the velocity function. Okay. And then it's taking the integral of your velocity function, the antiderivative of that, and doing it again. So it has to do two integrals. Right. It takes GC a really long time.
Right. So for every calculation of velocity, which is a whole bunch of calculations, right, to get each calculated velocity, then for each one of those, it's doing a whole mess of calculations to get the distance. All right, so this is just, it's kind of, it's branching out in amount of work that it has to do very, very quickly. All right, and you can read about that in 8.5. So that's having defined everything in what we call open form. So integrals, writing an integral function is an example of writing an open form function, meaning it reflects process. What? This process of accumulating bits of change, right? So integral from 0 to t, v1u du. That's reflecting this process of accumulating all those bits of little changes in distance using the rate of change function. And we see the disadvantage to that. The advantage is it reflects the process, which is really important, the meaning of it, right? But the disadvantage is, in terms of computation, you get a situation like this. And even a high-speed computer, it took a relatively long time to do that. So now in this file, I have those same functions, and I have them defined in closed form. So here I'm graphing, so now I'm calling S1C for closed and S2C for closed. Same functions, but... And what is closed form? Closed form is any function that's built on just the common functions, right? Common functions. Polynomials, exponential functions, sine and cosine, log functions, all these common functions. Any functions built from combinations of those functions or multiples or any way you could combine those algebraically is called a closed form function. And now I'm going to graph those. Ready? Watch. I'll do it again. So, what's the advantage of a closed form function? Right. Okay, so it's the idea of it's efficient in its computability. Very efficient, right? These polynomials, sine functions, all the trig functions, exponential functions, etc. They're all really super efficient in speed of calculation. And a lot of them we can just do by hand. We don't even need technology at all. Okay? So this is kind of that's a preview of what we're going to start doing here. So let's take a look at this. So what's the net accumulation of a quantity? That quantity is given by function f starting from x equals a. So where is Gabriel? R. Is Gabriel here? How about Carter, Hogan? Carter. So what is the net accumulation of a quantity given by function f starting from x equals a? What would that be? Okay, integral of f from a to x. Where is Anders? Anders Ray. You agree? Integral, he said.
Well, if you just make it x equal to a, that wouldn't really be going anywhere.
How about the integral of f? Do you agree with that?
Yeah.
What do we think? Is it the integral of f? Quantity. We want the net accumulation of a quantity. The quantity is given by f. So we want the integral of f? No, when we do integrals, what's the function that we have? Rate of change, right? Rate of change. So if the quantity is given by f, we want to write an accumulation function open form. We want the integral of the rate of change, right? The rate of change of f. Okay? If I said write the net accumulation of a quantity whose rate is f, if the rate was f, then it'd be the integral f. But if it's the quantity is f, then we want the rate of change of f. Okay, so now I want to write the function f in terms of this integral. So how can I write f of x equals using this integral? Where is Sean? So I want to write the function f of x equals, but I want to use this net accumulation starting at a as part of that function rule. How could I do that? F of x equals what? Okay, so this is what? This is all the accumulation where? Starting from a to x. So if I want all of the accumulation, if I want to write f, then I just need to include what? F of a, right? So I need all the accumulation up to a plus the accumulation starting from a. So f of x would be f of a plus the integral starting from a. Does that make sense? Right? We've seen this before. I wanted to refresh because I know we've been focusing on building these net accumulation functions. If we want the total accumulation, then we just need to include all the accumulation before a, and that's f of a. Okay? All right, so if we subtract f of a from both sides, then we get this. And what does each side represent now? F of x minus f of a is? So they're both exact net accumulation, right? We know that integral is exact net accumulation. It's equal to f of x minus f of a, so that's just another way of expressing the net accumulation, but in terms of just final minus initial, right? Final minus initial versus the accumulation of many bits of change. So this is all review. And when we, now this equation is our equation of the fundamental theorem, right? This is the fundamental theorem of calculus. It says that the accumulation of many changes from a to x is the same as the net change, right? The net change from a to x, which is final value of the quantity minus initial value. So now we're gonna use this. We're gonna use the fundamental theorem to write open form accumulation functions, like on the left, like we've been doing all semester, but in closed form. All right, so we're going to use this. So it's not necessarily true that f is representing a closed form, but that's how we're going to use it. We're going to be looking for a closed form version of little f, so that we can write the left side in term like the right side. And what again is closed form? What's closed form? Closed form, built from common functions that are highly efficient for computing, right? Built from common functions that are highly efficient for computing. That's what we want. So then the question is, how do we get the function f from R sub f? What will that look like? Who's next here? That is it. Alejandro, is that Alex? Jans? Yeah. How are we going to get little f from R sub f?
Take the antiderivative.
Okay, right. Why? Because we know the rate function is a derivative of the quantity function. So therefore, this quantity function f is going to be antiderivative, right? Antiderivative of R sub f. So that's this next week, couple weeks in the course, is we're going to focus on how do we find antiderivatives, closed form functions, versions of accumulation functions that we've been writing in open form. That means getting the quantity function from the rate, which is antiderivative. Okay, good so far? Okay, so here's some warm-up, or some easy ones. So closed form accumulation. So for each expression, you're going to work here with the person next to you. Explain the meaning of the expression, include all the specifics. We're all experts at that. And then I want you to write a computable expression using the fundamental theorem that gives its value exactly, or gives another version, I should say, gives another version of this function. I say a closed form version. And then simplify if appropriate. That's less important. So more important is parts A and B. We want to explain the meaning and then come up with a computable expression or a closed form version of the given function. You can work together, take about 5 minutes, see how these go. You need to turn your desks, get a little kind of close to each other. That's fine. So let's. So let's just. So that's what you're working with, right? So from A to.
Yeah, it was the accumulation of rate change cosine u. This one's on negative 1/2.
Okay. And are we accumulating rate of change? Is it accumulation of rate of change? Accumulation of cosine u? Are we accumulating cosine u? So cosine u, so you're correct that cosine u is a rate of change. What are we accumulating? What's getting accumulated? Okay, yeah, so there's some quantity, right? There's some quantity that's accumulating whose rate of change is cosine u, right? There's some quantity accumulating whose rate of change is cosine u. Okay, and then keep going, Cameron. Did you get the...
Negative sine x minus sine of negative, or minus negative sine.
So like this? So you were saying that the antiderivative of cosine is negative sine. Is that right? Is that what you were saying? And is that right? So let's try it. So how can we check when we're taking a stab at an antiderivative? This is going to be a huge theme. How can we check it? Take the derivative. Okay, so he had this conjecture that sine x is going to give us a derivative of cosine x. All right, so now just forget about this problem and go to negative sine x and say, what's the derivative of that? Is it cosine or negative cosine? Negative cosine. So, how do we do with negative sine? So yeah, so now we just go back and adjust. Just like, oh, we got a negative that we didn't want. So really we just wanted sine, right? We just wanted sine because the derivative of sine is cosine. So really what we wanted was, but no, this is really good because this is going to be like a key element to this. You don't have to get it perfect on the first try. Just go for it. Just go get something close, and then take the derivative. But when you take the derivative, you kind of got to clear your mind of the original problem and be like, okay, I'm back in 270. I'm on the mastery test. I've got to get this last one right to pass it, right? And then, okay, derivative of negative sine, that's negative cosine. Okay, no, that's not what I want. So adjust it. Derivative of sine is cosine. That's the one I want. Okay, so what do we just found? We found a new version of this function, right? These are both going to give the exact same values of the dependent variable. They're both going to give you exactly the same thing. This one, though, is closed form, right? This one is a closed form version, which is going to be a lot more efficient in computing outputs, right? Questions on the first one? Okay, next one. Where is John Maelstrom?
I just said the same thing, 3e to the w.
So you're saying, so the antiderivative of 3e to the x is just 3e to the x. Okay? So then what's the closed form of this accumulation function? So we got, look, remember? In order to get that net accumulation, we got to subtract off f of a. Remember that? So you got your f is your 3e to the x. So now we're just going to follow this. Okay? How about, where's Daniel? Yeah. Okay. So then what is this net accumulation function? Three e to the w? X, right? 3e to the x minus 3e to the 3e to the 0, and that's 0 because whenever you plug something in for 0, it's always 0. Okay, so watch out. That's an easy trap to fall into. Whenever you plug 0 into something, you get 0. Here's a good example. It's not, right? Another example is cosine. Plug 0 into cosine, you don't get 0. So just be careful. So 3e to the x minus 3. So there is our, there's a closed form version of this net accumulation function. Next one. So there's kind of two steps to this. There's getting the antiderivative, and then there's applying the fundamental theorem, which says that it's the net change from A to X, right? So you've got to get the antiderivative, and then you have to apply the net change that it's going to be f of x minus f of a. So antiderivative of t to the fourth. So what function, if we took the derivative of it, would give us t to the fourth? Daniel, or Andrew Eubanks. Where's Andrew? T to the fifth divided by 5. Right? Because we know this is the power rule, right? The power rule is going to decrease the exponent by 1. So now we're what? If we're doing antiderivative, we're going to increase it by 1. But then, again, do our test, right? T to the fifth, or x to the fifth. Take the derivative, you get 5x to the fourth. How's that different from what we have? No 5, right? No 5. So how do we adjust the initial attempt so that we won't have a 5? Divide by 5 or multiply by a fifth, either way. All right, so then applying the fundamental theorem, we got our t to the fifth over 5. Keep going. Okay. That's supposed to be a power. So we get x to the fifth, or 1/5 x to the fifth, minus 1/5. Okay. Did I lose anybody? Please ask if... So there's two things going on here, right? Antiderivative is what function, if I took the derivative of it using all the rules I learned in Calc 1, is going to give me that. And then the next thing is I got to apply the fundamental theorem, which says that the net accumulation from A to X is going to be the accumulation up to X minus the accumulation up to A. So I got to do both things, right? Both things. All right, last one. Volunteer. Yes, sir? Tell me your name. Micah.
2/3 times a squared plus 3 to be 3/2.
Okay, and tell me how you thought about that. So how did you come up with that?
I realized it was going to be the chain rule, and that when we're deriving, to get to our one up there,
okay,
we have to
no, you're doing great. That's hard to explain verbally. Yeah, no, you did great. So what he recognized was that this is the result of the chain rule. When you do the chain rule, remember, you do the derivative of the kind of in the big picture of the external function, and then you multiply by the derivative of the interior. So this one is totally rigged for that. Do you see that? That this is the result of having, this 2a is the result of having multiplied by the derivative of the interior function. And that's exactly what you do in the chain rule. So if we were to think about, we want to collapse it back together because now we're going backwards, what would happen? Well, we would have the kind of the antiderivative of this, which would be what? 2, this would be to the 3/2. And then you'd also need, so now we're thinking about deriving this, right? Taking the derivative. It'd be 3/2 times this to the 1/2. So we would need 2/3 because we don't have a power of 3/2 out here. Okay? And then that would be our f of x. And then, but what about the 2a? Well, when you take the derivative of it, then you, at the end, you multiply by 2x. Well, there it is. And then we're going to have that same function with 10 plugged in. Okay, if I lost you a little bit, it's okay, because that's just a preview of what we're going to kind of do a little slower now. We're going to work on harder ones like that. But that's the idea of this. You have to anticipate, you have to see this and say, oh, that's just the chain rule because that's the derivative of my inside. So when I do antiderivative, that's going to go away, right? That's going to go away. And we're just basically doing antiderivative of this thing. and cleaning up the mess. We needed a 2/3 to balance it out. Okay, so again, if you're not 100% there on that, that's okay, because that's what how we're spending our time doing now. So if we're going to understand this undoing the chain rule, then let's practice some chain rule. Let's just practice chain rule derivatives. Because really being good at this undoing the chain rule means just knowing the chain rule really well. So here's some chain rule derivatives practice. I've got H, Z, and capital B functions. I want you to do the derivative of these, right? The derivative of H, derivative of Z, derivative of B. And as a hint for H, start that one off writing it this way. So how could you rewrite H before you start taking the derivative? As something to a power, something to a power. Okay, but now, remember, we're doing derivatives now. This is like mastery test problems, derivatives. So take a minute or two to work on those. Okay, so they all follow this pattern of what? Rate of change of the exterior function, keeping the interior as it is, times rate of change of the interior, right? And they all follow that pattern. So when we're thinking antiderivative, we're looking for that pattern. We're looking for two functions, usually two functions multiplied. One is composite, meaning, and then the other one is the rate of change of the interior function. That's what we're on the lookout for. Questions on these answers? Everyone get those? You see, follow it? Okay, so let's so this is what we're thinking. We're thinking, how do we recognize something like that on the right and be able to attain or obtain the original function over there on the left? So you're thinking about the chain rule, but I also give you a little structure to a little method to the madness. Okay, so I'm going to give you some structure, but the goal is you see it and you recognize the original function. Now, if some of you may have done something called substitution or U substitution, we're going to try to avoid that. We'll really try hard, because if you get good at this, it can take 1/3 or 1/4 of the time of U substitution. And the same with the writing, all right? It saves you lots of writing and lots of time if you can get good at it. And the other advantage to it is it really reinforces your understanding of the chain rule. Okay, so we want to use our understanding of the chain rule to just be able to do it backwards and save all that extra fuss of U substitution. So just really try to go with it here. If U substitution is like your security blanket, see if you can let go. Okay, here we go. So here's the chain rule. So we got a function, a composite function. Derivative will be G prime F times F prime, right? So the rate of change of the exterior times the rate of change, or with the interior as is, times the rate of change of the interior. So don't really listen and don't try to copy everything down off the screen. So just really listen. If you want to get good notes, you can watch the video later. So antiderivative is going to look like this. It's going to be flipped. We're going to be on the lookout for something of this form, G prime F times F prime, and we want to collapse it back into the original function. So given this function over here, what are you going to focus on in your given function if you want to recover the amount function g of f of x? Are you going to focus on the g prime f to get g of f, or are you going to focus on the f prime to help you get g of f? What does g of f look like more? Right? What are you going to focus on? Exhibit A or Exhibit B? It wasn't resounding. So if we want g of f of x, what's going to help you get g of f of x better? G prime of f or f prime? G prime of f. See how close they are? Right? So this is essentially, it's just one step away from the answer. Right? What do? What will the approach be? We're going to write the antiderivative of the exterior function g and keep the interior function f as it is. And we're pretty much done. That's the most of it. We might have to clean up like a factor. There's a little bit of a mess with the factor, okay? So we might have to get like some factor out in front, right? But this is the main thing. If we can figure out which part is the g prime of f, then we figure out what the g prime is, then we just need to do the antiderivative of g and keep f the same. Check it by taking the derivative and see if we need an extra factor in there. Okay, let's try some examples. First one. X cubed times 8 plus x to the 4th to the 5th. So, we're going to think this is like g prime f times f prime, the result of a chain rule derivative. And we need to recover the original g of f. So what are we going to focus on? Are we going to focus on the x cubed or the 8 plus x to the 4th to the 5th? So exhibit A or exhibit B? What's going to be our focus? What's our g prime of f? Exhibit A or exhibit B? B. And how do we know that this is undoing the chain rule? Because x cubed is essentially the rate of change of the inside. It might be off by a factor, but factors are no problem, right? So x cubed is essentially the rate of change of the inside. That confirms we're going to undo the chain rule, and that's our g prime of f. So our first attempt at this will be g of f, right? If that's g prime of f, we want g of f, meaning antiderivative of the external function. What's the external function in this case? To the 5th. Antiderivative of something to the 5th is to the 6th. But then we would need 1/6. So we're going to call that our first attempt. And now we're going to check it. How are we going to check it? Take the derivative. Okay, now we got to kind of erase all this stuff out of your mind and just now we got a new problem. Here, it's this right here. We're going to take the derivative. What is it? 6 times 1/6 times 8 plus x to the 4th, all to the 5th, by the chain rule, times the rate of change of the inside, 4x cubed. And so, is this exactly the same as what we started with? If it is, we're done. We got it on the first attempt. Is it? Not quite. What are we off by? It's 4. So our antiderivative was 4 times too much. So how do we adjust our attempt so that 4 is not there? So then we just need another 1/4. 1/4 times 1/6. 8 plus x to the 4th to the 6th. And then that's 1/24. If you're not confident with what you did, what can you? So now we've got this as our second attempt. What can you do? Take the derivative, and if it should be exactly what you started with. Okay, so I want to point out that so that's a different topic. So any questions on this first? Yes, ma'am.
Wouldn't we have gotten rid of the 6 times 1 to the 6 or 1/6 because it would just be 1?
Yeah, so 6 times 1 to the 6 is 1, that's right.
So why did we carry it down and multiply the 1/4 times 1/6?
Because that was correct. I mean, that was fine. The 1/6 was fine. It helped us get rid of the 6. So we're good with the 1/6. But then what was different about this from the original was this extra factor of 4. So all we're going to do is take that first attempt and adjust it by 1/4. So I don't want to get rid of this 1/6. It was helpful. It's part of it. So we're comparing in the check. We compare that with that, and we say, how are they different? How did I miss? I missed only by 4. So then I'm going to take that first attempt and adjust it by dividing by 4. Yeah.
A little confused. Wouldn't it be better to write the 1/4 like inside as a factor on the x to the 4th?
No, because that's totally different than I'd get just x cubed here. But if I wrote the 1/4 inside, then I'm not going to get this derivative. This is its derivative, because this doesn't have a 1/4 inside. You see?
Oh, okay.
Yeah.
I see it.
This is whatever you end up with. Its derivative has to be this. So if you have a 1/4 inside, that's not going to work. Yeah. Other questions? Good questions. Yes, sir?
Would the 8 have an X on it?
No, because remember the chain rule says then take the derivative of the interior, which would be 0 plus 4x cubed. So if we had 8x, then you'd have something like 8 plus 4x cubed as this thing. It's only x cubed, so that needs to be just the constant 8. Other questions? Yeah, so again, the key thing is check. Take the derivative. When you take the derivative, you'll see where your error is and comparing it to the original. Okay, so I need to point something out. Every time we've set up these net accumulation functions, we always had what? It's like from a to something, x. Well, we're using x here, so let's say a to t, okay? If you see an integral with nothing, what does that mean? That means all antiderivatives, right? So starting from any value of a, right? So it's the net accumulation starting from any value of a. Okay? So what we would have is then we'd have like minus f of a. This is kind of like implied. But f of a is just a constant, right? So minus f of a, we just have to account for that. And so the conventional way to account for that is to say plus c. And so c, the constant, is the opposite of f of a. And by adding the plus c, we're saying every possible accumulation function that has this as its rate of change. So when you see nothing, it really means all accumulation functions starting from any a. And so we generically say plus c to mean this minus f of a part. Is that okay? So like in your homework, the homework's on web work, and so you're going to see that. Sometimes they'll give you the box like this, and then they'll have the c, so you don't have to put the c in. But sometimes they don't give you the c, and so in your answer you have to have the plus c. Okay? Just be aware of that.